SimGen is a domain-specific language that runs embedded in SWI-Prolog. It won't run on its own. You have to call it from SWI-Prolog. It's used to create simulations of behavior. It's a behavior language. Similarity's business is anomalometry. Anomalometry, you know this phenomenon where, like, you're driving your car and it doesn't sound right, and it's just making a funny noise, and you don't know what's causing it, but you very much understand your choices are go to the mechanic now or be towed to the mechanic next week. Yeah? Now, suppose you own an oil rig and you have a gigantic pump on the oil rig, and you really would like to know when the pump starts making funny noises. And it turns out you can make computers really good at doing this, so that you can make a detector system that'll start saying, think about maintaining the pump, long before the pump actually fails. So, why did we need simulations? Why couldn't we just, like, work from live data? Well, often we didn't have data. Companies are really reluctant to give you data until you've done all kinds of things, one of which is prove your system will work with their data. There might not be enough data. What if the pump's just being installed? It might not be the right data. What if your pump has never failed? So, and we needed to develop the system, the anomalometry system, and that meant we needed to be able to create data when we knew the underlying system driving the data. So, we built SimGen. SimGen is a behavior language. So what's a behavior? Well, a behavior is a pattern of activity over time. So buying groceries is a behavior. Checking out is a smaller behavior that is part of buying groceries. Picking out the fish is a smaller behavior that's part of buying groceries. SimGen models the world as a hybrid system. Now, how many people here know partial differential equations? At least somewhat. Yeah? Okay, good. Models the world as a hybrid system. In a hybrid system, you have a partial differential equation that models your world up to some boundary condition. Remember boundary conditions for partial differential equations? Yeah, don't worry, we're not going to do lots of partial differential equations here. But at that boundary, something happens, right? And that's discrete. And as computer people, we usually spend more of our time worrying about discrete computation, right? That's where all the interesting parts are. Okay, here's an example of such a system. A ball bouncing on a floor. The ball flies through the air, and as long as it's in the air, it's going to follow Newton's laws of motion, right? It's going to accelerate downwards, and so it's going to follow a parabola, blah, blah, blah. And then it's going to strike the ground. At that point, its behavior changes. Now, it engages in elastic rebound. On the right, you'll see I have This is a node model, which is how we model things in SimGen of the bouncing ball. This is a loop, which says, hey, it's going to do the activity below me over and over. And that activity is two things in succession: fly through the air, hit the ground. Okay? Here's some examples of things you might reasonably model using SimGen. A non-player character for a game. In fact, our inspiration for this was behavior trees from games, from game AI. Anybody here make games have you used behavior trees for AI? Yeah? Cool. Much of this is going to look very familiar. Artificial agents. These things were popular a few years ago. The idea was, I need to get data off of a bunch of servers, so I'll send each one an agent, and it will autonomously do whatever it needs to do. So artificial agents are a possible use. A system simulation, this is the case Simulary wrote the thing for. System control. Well, we could be simulating, but if we provided inputs from the real world and monitor the simulation and use it to control the real world, we can build a controller for the real world. So we're launching a rocket. We need to do all the steps in the pre-launch countdown and do lots of checks. We could do that with SimGen. Or we might have a particularly complicated process. Let's say you have some website that deals with medical stuff, and you have to get permission to get the patient data, and you have to get like some legal release, and then you have to get a bunch of other information, and it gets really complicated. You could treat the whole thing as a simulation. Here's a more complicated example. This is an evening out. Now, one thing I'd point out here is, frankly, I just wanted a simulation that took up, a slide. So notice that while I put quite a bit of detail into how people get to the meeting point, eat is, going to a restaurant's pretty complicated behavior, but I'm not interested in the details of what happens in the restaurant. We're just going to eat. So I'm not modeling that. That's always true with simulations, is you have to decide what to simulate, right? We're not going to simulate where on Alice's car's brakes, right? Because we're not interested in that here. Okay, this is an abstract plan for an evening out, right? We're saying we're going to do a bunch of things in sequence. We will do some things in parallel. Each person will get to the meeting point independently. So we can just run those in parallel. And then we'll have a single unit walk to the restaurant, eat, go to the movie, and then again we'll all split up into independent groups, and we will go home. Okay? Everybody with me? Yes? Okay. This is this is somewhere early in the evening, and some nodes are running. They're in the process of having their evening out, but they're still all going to the meeting place, okay? And Alice is driving downtown. Bob has not left your work yet, Carol's walking to the meeting place, right? So eventually, you know, like Carol will reach downtown, and then these will be done, but we'll still be waiting for the other two people to get there. Yeah? So we call these the active nodes. Nodes start and stop, right? Carol gets in her car and drives downtown. That has a finite duration. Nodes can be in the not started state. When they're started, then they're in the started state. They then stop or die somehow, and at that point they're ready to be restarted. But there's three ways a node can die. One is to be done. To be done is just to have successfully finished the task. Alice is done when she gets downtown and parks. It could fail. Alice's car breaks down. She's called home for an emergency. Alice fails. Now, when I shut off my car, everybody have a mental model of me pulling into my driveway and shutting my car off, okay? Does your mental model include the fact that the fuel pump will stop pumping? Not really, right? Behaviors, larger behaviors, often are composed of hundreds of smaller behaviors. And when we stop the larger behavior, all of those smaller behaviors stop. In a car, for example, not everything stops when you turn the key off. Most modern cars have an electric cooling fan, and when you turn it off, the fan keeps running for a while to cool the engine. Yeah? So you would have to have some higher level of notion of off. Because, but you could still say, here's the key, and when the key turns off, the water pump stops, the engine stops rotating, and so on. As a result, we have this one, terminated. When the higher level stops, we terminate the lower level node. Here's a parallel node. It's trying to do A, B, and C in parallel. C, in turn, has started D and E. So everything's running along, and A fails. When A fails, the rule for a parallel node is if any of its children fail, it fails. So we're going to fail the root node, this parallel, right? But first, we must stop everything below it. So we'll send terminate messages down. We'll terminate B, that's fine. When C gets a terminate message, C has children. So C must terminate D and E before it's allowed to stop. Its children terminate, now it's allowed to terminate, and now all the children have died, and the parallel is allowed to die by failing. Okay, questions about that?
Could you give constraints that you say that the root node fails, there has to be two children to fail? In the other case,
you could build a different root, a different node type. What you would do normally here is you would have to say, you just build it out of pieces. That sounds really hairy, and frankly, if I actually needed that kind of thing, I would stick another node in the language.
Okay. But it would be possible in principle.
It certainly is possible in principle, but we don't really have a N must be running node. I'm not certain what you do. What would you need that for?
Just I have something in mind.
Okay, this is a different view of the same thing. This is a view of the kind of the data model. You might have a number of, let's say we're modeling an industrial process and we have 25 identical pumps. I don't want to like have nodes labeled, you know, pump 1, pump 2, pump 3, and so on, right? We're computer science people and understand why we don't want that. So I provide contexts. When you start a simulation, nothing's happening. Then you start a context. And you can start as many of these as you want. Each context gets its own clock. It typically starts at 0 when the context started. It gets a set of variables, which are floats. It gets a set of guards. I also call them conditions, which are Booleans. And then it has some set of running nodes. And when you start a context, you're allowed to give the name of one node, which it will start. Now I'm getting faces. Questions? Folks are good?
Yep.
Happy?
Yep.
Happy. Okay. So Prolog, from Prolog, we can actually modify these variables and guards. All right. So how do you use this thing? This is the conceptual model, and now we're ready to talk about like nitty-gritty. You can load. You specify the simulation in a language called BT in a BT language file, which you then consult into your program. Consult is Prolog's word for load. So you load it in. I'm going to go through the syntax of the BT language. A BT file is just a series of node definitions. Is that a question back there? Nope. Okay. It's just a series of node definitions. There are two kinds of node definition. This top one is a named node, and everything at the top level must be a named node. It has a name, which is a Prolog atom. An operator, there's a predefined set of operators. A bunch of stuff that is, whose format depends on the type of operator, and a period. Each node is like that. Okay? One common thing in stuff is a child or children, right? We have the arrows, so obviously you have to name who your children are. So there's a second kind of node, an anonymous node, which can be written any place the name of a node can be written. So in some sense, it's like a lambda. And it doesn't have a name, but it has an operator, and then the same set of stuff as a named node. And then there are comments. Okay. since most of the syntax depends on the kind of operator, I'm going to run through the operators. This first one says randomly run one of your children. Yeah? You're making a non-player character and you want it to say something, but you don't want it to always say the same thing. That'd make it look really stupid, so you randomly pick one of a half dozen things.
To execute. To execute. You're executing children. It's like having drove back.
Yes. You're going to have a sequence of things that you do in sequence. If one of them fails, well, you're not going to do the rest of them, right? This is basically maybe mode. Sorry about that. You can first scramble the order and then execute the children in order, in the scrambled order. This is parallel. There are two kinds of parallelism. There is concurrent and, which means run all your children, and then if any of them fail, the whole thing fails. When they all get done, you do a join, and once they're all done, then you return. An odd use of this is to guard a condition. If you run a check for a condition in parallel with what you're actually doing, like I check that the coolant is on, and then I run the tool. So if the cooler fails, then the tool will stop. There is also competitive OR. Run the children and then terminate the others when the first one succeeds. So I am going to make 4 attempts to like get through to something. And as soon as like one of my workers picks it up or whatever, then I can dismiss the other situations, the other children. This is the check guard that you use with the parallel. Every tick, it just makes certain that its condition is true, and if not, it fails. You can also have it. You can also wait. This isn't done until the condition becomes true. And then you can set and clear conditions. So there's ways of communicating laterally across the tree. Sometimes you don't care whether something succeeded. Try will just wrap it in ignore the result. You can just fail, not. Dir just waits. Oftentimes you just want to, especially, for example, in our eating out, in our evening out example, if I am not interested in simulating the restaurant, I can just put in a duration, right? That we take an hour and we have our meal. Pin is a similarity-specific thing. It's not worth going into. And then there are two ways of restarting. There is a loop that just repeatedly restarts its single child until the child fails, which is often never, and a retry loop, which will keep retrying its child until it succeeds. And okay, I said that it was a hybrid system, that we modeled hybrid system. this bang operator, also called the partial differential equation operator, is for modeling the continuous part. At the moment, we're not actually running, we're not actually like symbolically solving partial differential equations. It's on the roadmap, but SimGen's in a really early state. So you put in a series of assignment statements, which are the first ticks, which happen on the first tick, a series of assignment statements that happen on all other ticks, and a condition, which is at the bottom. This is an odd way to make a loop, and it's done this way because it makes writing bias-free integration far easier. There are two forms, darn it, there are two forms of assignment. One is, give me the values from the last cycle. This is, if you're going to propagate forward, something's got to do this, but you have to pick that carefully so that you don't get bias. And then the other is data flow, which waits to execute until everything on its right side is available. And the operators on the right-hand side are all the operators. If you don't know Prolog, Prolog does not evaluate its arguments. So that means if you write 1 plus 2, you get a complex term of whose functor is plus and arguments are 1 and 2. You don't get 3. If you want 3, you have to use the is operator. And the PDQ node provides you with all of the operators and functions that are available to the is operator, and additionally provides you several noise functions. Levy flight is a noise function that tends to have jumps in it. And so this blue line is Levy flight. And you can see it's random, but it's different than the second one, which is wander. Wander makes a value wander between two bounds. The rest of these, well, there's clock, and then the rest of them are simply moving off of Prolog operators that conflict with the SimGen operators. That's the BT language. Is there questions?
Is it an embedded language in Prolog, or is it like an external ESL?
You have to run it from within Prolog.
Okay.
You can't just execute SimGen on its own. Basically because we wanted to keep the language very simple because it actually has nice mathematical properties. And those properties would go away if we did a whole bunch of other kind of effectful things. So we basically say, if you want to do all those other things, you do them in Prolog. I'm going to talk about how to interact with Prolog now. And yeah, I'm at 29. Okay, you start a simulation, give it some numbers. You can get user time coordinates, so you don't have to work in nanoseconds, which are hell. And then you start context, right, from Prolog. So Prolog contains library broadcast. This is part of the Prolog distribution. It provides pub/sub. You can register for a listener, and Prolog's a logic language. It does unification, so you can get a message. It will fill in some of these values, and then you can pass them to your handler. here's the kinds of messages you can get. A reading is emitted every time a value changes. Starting and stopping of nodes. And there's every tick, you will get a tick message. This tick carries along, you're allowed to provide a state object when you start the simulation, and then when you get the tick, it will carry it back. So if you are doing some other sort of simulation that's not easy to do in SimGen, you can do it along here and just generally thread state through your Prolog. Okay, you can interact with the system by setting and clearing guards and setting and reading values. And that's pretty much SimGen. In the future, we're going to change variables to vectors from reals so that we can work in RN. We are going to change the bang node syntax, probably provide a new operator that allows you to set up a real partial differential equation. And I'm seriously considering dropping having special syntax. So BT language might go away, and instead you might provide a Prolog term. Questions? Do we have questions? Yes?
So the ticks, are they based on events, or is there like a clock?
There is a master clock maintained by this. The question is, are ticks events, or are they from some master clock? Yes, the simulation is provides a master clock and provides a clock for each context. Of course, they move forward at the same rate. Other questions? Other questions? One up here.
Would it be possible to, let's think we have a simulation, completely different setup. In my case, autonomous driving, you simulate a car in a traffic situation.
Okay.
Yeah. And then on the other side, you describe with SimGen and behavior the car should show. Could you use SimGen to check the simulation results against the behavior?
Yes, you certainly could.
Okay.
Sure. I mean, there's some details in that, any book on simulation will cover that. Other questions? Other questions? Everybody's happy? Everybody's bored? Everybody's confused? There's
Why
one back
not
here.
all three? Just a sec. No.
No.
Shouting will not be recorded.
Shouting won't record.
You showed an example earlier of a simulation tree that fitted on a slide. Is that representative of the kind of size of the simulations you're building, or are they much bigger and more complex?
They're often somewhat larger than that. I've had some. That's probably like the lower end of a realistic simulation. What gets complicated is that simulation's not much use on its own. It would be far more useful to do if it contained a bunch of situations like Alice's car broke down that could happen randomly. You start sticking random nodes in, and you start asking questions. And in fact, something we hope to one day do is be able to ask questions like, what is the probability that they will actually get through the evening successfully? More questions? I didn't. Oh.
Hello. I really like the talk about how to build a simulation, Do you have advice about how to prepare the simulation? So what are the parts that you want to simulate? What are the parts that you want to leave out?
Basically, have your questions in mind when you build the simulation. If what we're really interested in is Alice's heart rate, this is probably not the simulation we want. It may not be what we want Alice to be simulated doing. It may also not be what we but it also just doesn't model the factors that we're interested in for that. So it's all driven by what questions do I want to ask? What do I want in my output data? Ultimately, this thing, for all of our use cases, this thing just makes a CSV file. And so that, am I answering your question? Okay. There's one way in the back.
Way in the back. What?
By the cameraman.
Thank you for a very interesting talk and this extension to Prolog. Coming to this talk, I was divided because this John Hughes...
About what?
Divided about the talk. There was a talk about FP doing quick check, like property-based testing.
Oh, yeah.
Which is basically having randomly generated facts and probabilities and all that.
Sure.
In the end, had to simulate whether the program type checks with those examples. This is basically a model of, but not using types, but definitely there is a common subset in both approaches and both.
Are you asking if that's a valid thing to do?
No, I'm asking maybe if there are people trying to mix those, or what's your ideas on that, or pointers to?
I mean, it seems like SimGen would be a good tool for some things. After all, it was essentially built as a testing tool. Mm-hmm. It was built so that we could do things like a very, very common model for us to work with at Simularity was this pump is either an A or a B. If it's an A, it operates normally. If it's a B, it slowly gets worse. And gets worse at Simularity often has to do with spectra. That kind of thing. Simulators in AI shop, and of course, and stability as you change the inputs is very important. So many of the testing techniques are essentially fuzzing. Yeah, and the big clock on the wall says I should stop. And so I want to thank Liz Durr and Ray Richardson. Liz authorized making it open source. Ray was very helpful when I was building it. And the code's available on GitHub on Simularities.
All right, thank you, Annie.